Welcome back. In this section, we'll be using a set of techniques called unsupervised learning techniques in order to dig into and really understand your customer data, as well as any other data that you want to analyze using these techniques. The techniques are very general and can be applied to many areas of your business. In this video, we're specifically going to define unsupervised learning, understand what it means to apply it to data, and then learn our first unsupervised learning technique called K-means clustering. Based on the name, you might think that unsupervised learning is the opposite of supervised learning. And it is true that it doesn't have supervision. That is, it doesn't have any ground truth labels or information about what the output of the unsupervised learning algorithm should be. But supervised learning and unsupervised learning are fundamentally trying to solve different problems. Supervised learning is about taking existing data and making predictions based on it. So given some example inputs and example outputs, can we produce the right outputs on new inputs? This is really useful, for example, predicting the future or filling in missing data, things that we don't know about a customer but that we might be able to guess. Unsupervised learning is fundamentally about summarizing data. It's about generating insights into a static data set. We're really just interested in examining the customers we already have and understanding the sales that we've already made. How can we summarize these in a way that helps us to get insight into how our business works, who our customers are, and maybe think about what we could do to better serve them? Because we don't have any ground truth of what we want to output, we could think about, what if we made up the output? What if we knew there was some output, but we don't know what it is? What would it be? So in this example, we have some different data points, and we have two dimensions that describe the data points here, the horizontal and vertical dimensions. And we want to know, if we were to predict some output, what might it look like? Well, one idea is that we could give these different labels, here represented by colors. And these three different colors represent three different groups. You could think about this as being analogous to creating classes in a classification problem, only here we don't actually know what the classes are. This idea of generating class labels given data set is called clustering. And it gets that name because we want to take grouped data or clusters of data and give them all the same label or apply the same class to them. So there are a number of things that you might be trying to do when you cluster. The first thing is that you want the clustering to be an accurate representation of the data. If I group, for example, all of the points together, and then I tell you, say, the average of each of the dimensions, this might be actually highly inaccurate. There may be no points in the dataset that have those exact properties. As an example, if I have a business that caters to very young people and very old people, and then I try and summarize the data by taking the average of their age, I'm going to think that all my customers are maybe 30 or 40-year-olds, when in fact all of them are really young and really old. And so I won't be able to serve my customers well if I don't have this accurate representation that they're really two different groups that have these distinct properties. At the same time, we do want to summarize the data. We want to create a simple explanation or summary that doesn't require us to look at every single data point. So, for example, it might be useful to have different groups based on the age of the customer. It probably wouldn't be useful to create different groups for every month that anyone had ever been born in, starting in with your oldest customer. In other words, it doesn't make sense to group people by their exact birthday, because then you're just creating a really long list of groups, and it really doesn't tell you that much in terms of summarizing the data. You still have to look at a lot of information. The last thing is that we want an algorithm that runs fairly quickly. We could imagine spending a lot of time trying to come up with the perfect way of clustering the data, but in reality, it's going to generally be better to get some information quickly than to get perfect information 10 years from now. So here's a really simple idea. If points are close together, we should try clustering them for our clustering algorithm. And an algorithm that is based on this idea is the k-means algorithm. It has a couple of different pieces. First, we imagine that there are k different groups. And for each of these groups, we're going to imagine that it has some center or some centroid. We're going to assign data to the center that it's closest to. So for every data point, we look at all of the centers and we see which one it's closest to. We assign it to that group, and at the end, we have k different groups of data. Well, now, because we've assigned this data, the center may not accurately describe the data anymore, so we're going to recompute the center as the mean or the average of all of the points in each cluster. Once we've done that, the means have moved a little bit, and we may want to reassign the data to a mean that may have gotten closer to it. So we'll repeat this process a few times, and eventually this will converge to a stable setting of centers and point assignments. So let's see how this looks in practice. I've provided some data for you, and remember that all of this code is available as well. Definitely feel free to play around with it and maybe extend it on your own data sets. But here we have data where different customers have bought different numbers of books in some different genres. So we can see the first record that I've loaded in here. This customer bought 42 different books, and we have both a count and a proportion of the books that they've bought in each genre. Now, for our purposes, we probably don't need all of these dimensions. If we have the total number of books bought and the proportions of books that they bought, that's probably enough information. That's actually definitely enough information for us to reconstruct the exact counts of how many books they bought in each genre. So what we're going to do is pre-process this data where we only pull out the fields that we care about, the total number of books, and then the proportion from each of the genres that we're considering. In this data set, there are 6 genres. It doesn't really matter what they are for the purpose of exploring the techniques, but you can see that some of these genres might be related, or some people might prefer some genres over other genres, and that's sort of what makes this data interesting. So once we've pre-processed this data, we're going to load the k-means module from scikit-learn. And the way that we create the clustering is really simple. We instantiate a k-means object. We have to tell it the number of clusters that we want. We use the fit command to create clusterings on our data. And then we can actually see what the centers of those clusters are. So here you can see with 2 clusters, it looks like most of the fields are pretty similar. The means are really similar. They only really differ in this first dimension, which is the number of books bought. It looks like we have 2 big groups of customers. One group buys a handful of books, and the other group buys almost 10 times as many books as that. And this is useful information. This tells us that our customer base, we have some sort of casual customers who come by and read a few books, and then we have some really avid readers. Or maybe they're customers who run libraries or bookstores or something where they would be buying a lot of books at once. So there's the question, how do we know that 2 clusters is the right number? What if we changed it to 3 or 5 or 17? How would we know whether or not we found the right number? If the data is really low dimensional, you could imagine plotting it and actually trying to see how many clusters there are, but we can't really do that with 7-dimensional data. So another technique is we can just try a bunch of different settings. We will change the number of clusters and then look at how good the clustering is. So for k-means, I've made this plot where we can see that increasing number of clusters allows us to reduce the distance between points and their centers. That's what this y-axis represents. So this gives us a sense that as we add more clusters, we are able to get more accurate to the data, but it looks like it's a pretty smooth curve. In particular, if there were a sort of right number, we'd expect there to be a kind of sharp cutoff where it improves really rapidly, and then after that, it barely improves at all. Because we don't see that, it may be that One, our data doesn't have well-defined clusters, and just partitioning it into more groups is going to be useful for us, but only up to the point that we can really analyze each of the clusters in turn. Another possibility is that k-means just isn't the right algorithm to produce the clusters. There may be some underlying structure that we're not really able to get at using k-means as a technique. So let's try and examine one of these clusterings so we can sort of figure out maybe which case it is. If we look at this clustering with, say, 5 clusters, this is just an example that I pulled out because it has most of the performance of having more clusters, but it's still a pretty small number, and we can check each mean. We see that there's still not a lot of variation between the different clusters in the proportion of each type of book bought. There's a little bit in that it looks like this last one, maybe they read a lot of these last 2 genres, which I think are science fiction and fantasy, compared to the other groups, but it's really not that much. What does seem to be changing is the first entry. That's the number of books that they've bought. We basically have 5 different clusters based on how many books they bought on average. And this is actually giving us a huge amount of insight. Because k-means computes the distance or the error of the clustering based on Euclidean distance of all of the dimensions, it means that dimensions that are larger than other dimensions, that is, they have a larger range of values, are going to be the most important to the k-means clustering algorithm. Here, all of the proportions are bounded to be between 0 and 1, and on average they're like a sixth or something. In the case of the number of books bought, the range seems to go from only a few up to more than 60. And that range is so much more significant to the distance metric used by the k-means algorithm than any of the proportions. And that's why these groups are really only splitting the data on this one dimension, the number of books bought. We could imagine doing some pre-processing or something that shrinks the dimensions that are too big so that we get better clusters. But it's going to turn out that there are some other things we can try first that sort of take care of this automatically.